Recall the definition of the conditional probability of an event A given an event B, which we define to be the probability of the intersection of the events A and B, normalized by the probability of B. Using this definition requires that the probability of B is not equal to 0. But what if the probability of B is equal to 0? That is, how do we define conditional probabilities when the events being conditioned on have probability 0? As an example, consider the problem of choosing a point uniformly at random on the unit square. Here, the x-coordinate and the y-coordinate constitute a pair of random variables, or a random vector. As an example, let's consider the event that the point xy lies exactly on the diagonal, meaning that the x and y coordinates are equal. While the diagonal shown here is illustrated as having non-zero width for emphasis, the true diagonal has area 0, and so the probability of this event is also 0. If we wanted to calculate, say, the conditional probability that the x-coordinate is larger than a half, given that the chosen point is on the diagonal, we would need to condition on an event of probability 0. In fact, whenever we want to condition on events concerning continuous random variables, we'll often have to work with events of probability 0. Our solution to this is to define this probability as the integral of a conditional density, where the conditional density is given as the ratio of the joint density of x and y and the marginal density of y. But where does this definition come from? In this video, we'll start by deriving this definition from scratch. We'll see how it arises as a result of conditioning on events with small probability and taking limits as their probability goes to 0. We'll also see an example of how solving the same problem in two different ways, both of which are completely correct, can lead to two different answers. This is an instance of Borel's paradox, which arises as a consequence of our definition of conditional densities, and illustrates some potential dangers of conditioning on events with probability 0, at least without being careful. To derive the formula for conditional densities, let's start again by considering the event that x is less than or equal to little x, given that y is equal to little y. Of course, what we would like to say is that this is equal to the probability of the intersection divided by the probability that y equals little y. But this definition doesn't make any sense because the probability in the denominator is equal to 0. Instead, we'll condition on the event that y is in the interval between little y and little y plus some small delta y. Since the event being conditioned on here has positive probability, we can use our usual definition to write this as a ratio of probabilities. Now, write these probabilities as integrals of the corresponding density functions. We use the joint density of x and y as the integrand in the numerator, and the marginal density of y as the integrand in the denominator. Now, moving the bottom integral inside and multiplying by delta y over delta y, which is just 1, we can apply the fundamental theorem of calculus to the terms in the numerator and the denominator to conclude that the integrals converge to the densities evaluated at v equals y as delta y goes to 0. If we define the conditional probability that x is less than or equal to little x, given y equal to little y as the following limit, we recover our original definition. To summarize, we condition on the event that y equals little y, an event of 0 probability, by instead conditioning on the event that y is in an interval close to little y, and taking limits as the size of that interval goes to 0. Okay, so now that we've done the hard work of understanding where our definition of conditional densities comes from, let's explore an interesting consequence of this definition called Borel's paradox. We start by choosing a point uniformly at random on the unit square, the square of side length 1 with its bottom left corner at the origin. The pair x, y is a pair of two random variables, or in other words, a random vector. Since x and y are uniform on the unit square, which has area 1, their joint density is just 1 on the unit square and 0 outside of it. This means that we can get the probability that the point is in some region A by integrating this density over the region. In this case, we're interested in the event D, that the point x, y lies on this diagonal. In particular, we want to compute the probability that the x-coordinate is larger than a half, given that the point lies on the diagonal. In what follows, we'll look at two different ways of calculating this probability. First, we'll define a new random variable u, which is equal to the difference between x and y. Observe that our point lies on the diagonal precisely when u is equal to 0. So we want to compute the conditional probability that x is larger than a half given that u is equal to 0. To do this, we'll need to compute the conditional density of x given u, which, as we've seen, is equal to the ratio of the joint density of x and u and the marginal density of u. We'll first compute the joint density of x and u. We can write the pair x comma u as a function of x and y, called t, and then use the change of variables formula to find the joint density of x and u. In this case, since the joint density of x and y is just the constant 1, and the absolute value of the determinant of dt inverse is also 1, then we just get that the joint density of x and u is 1. So far, we've established that the conditional density of x given u equals 0 is equal to 1 divided by the marginal density of u at 0. Now, what's left is to actually calculate the density of u. We can do this using the convolution formula. In doing so, we get that the density of u as a function of little u is equal to 1 minus the absolute value of little u. The distribution of u is also called the triangular distribution, so called because of the shape of its density. Finally, we can conclude that the conditional density of x given u equal to 0 is equal to 1. Now, to compute the probability that x is larger than a half, given that u is equal to 0, or that the chosen point is on the diagonal, we can just integrate this density over the corresponding interval, and our answer is 1/2. Now, that was a lot of calculation to find out something you could pretty much guess just by looking at a picture, since the x-coordinate is larger than a half on, well, half of the line. Now, let's do this computation one more time, but another way. I know what you're probably thinking, but I promise it'll be worth it. Previously, we defined the diagonal as the event that the difference between the x and y coordinates is 0. This time, we'll define the diagonal as the event that the ratio of the coordinates is 1. Notice that this is a completely valid way to specify the points on the diagonal, and the two events u equal to 0 and v equal to 1 are exactly the same, and both are equal to d. As before, to calculate the conditional density of x given v, we'll start by calculating the joint density of x and v. We can write x and v as a function of x and y, and again use the change of variables formula to get the joint density of x and v. This time, the Jacobian determinant of t inverse is x, so we get that the joint density of x and v is equal to x on the region pictured in part on the left. To compute the conditional density, we'll also need to find the marginal density of v, which we can get by integrating out x from the joint density. We can compute this integral by splitting the domain into two parts to get the following. Finally, we get that the marginal density of x given v equal to 1 is equal to 2x, and if we integrate this density to compute the conditional probability that x is larger than a half, we get 3/4. Wait, what just happened? We computed the same quantity, namely the conditional probability that x is larger than 1/2, given that the point x comma y lies in the diagonal, in two different ways, and got two completely different answers. The only difference between the two approaches was in how we described the diagonal event. In one case, using the fact that the difference between the x and y coordinates is 0, and in the other, using the fact that the ratio of the coordinates is 1. Both the event that u is equal to 0 and the event that v is equal to 1 are equal to the diagonal event, so it really seems like we should get the same answer either way. Could it be that we made a mistake in our calculation somewhere? No, it turns out that both of these answers are completely correct, and are actually a consequence of our definition of conditional densities. Recall that when we condition on the event that u is equal to 0, we're actually conditioning on the event that u is in the interval between 0 and some small delta u, and taking the limit of the probability as delta u approaches 0. Let's look at the event that u is contained in this small interval. Notice that this is equal to the event that x is between y and y plus delta u. If we draw this event on the unit square, we see that it corresponds to the region between the two lines y equal to x and y equal to x minus delta u. The conditional probability that we're interested in of the event that x is larger than a half corresponds to this highlighted region, which takes up about half of the total region in purple. Indeed, as delta u approaches 0, the ratio of these areas converges to a half. Let's now look at the second event, the event that the ratio y over x is equal to 1. In this case, we're conditioning on the event that the ratio v is between 1 and 1 plus delta v. We can see that this is equal to the event that y is between x and x times 1 plus delta v. If we now draw this event on the unit square, we see that it corresponds to the region in purple between the two lines y equals x and y equals 1 plus delta v times x. This time, the conditional probability of the event that x is larger than a half corresponds to this highlighted region, and we can see that it takes up a much greater proportion than half of the total purple region. As delta v converges to 0, the ratio of these two areas converges to 3 over 4. Also, notice that as x increases, the height of the vertical cross-section of values of y inside the region increases as well, which explains why the conditional density of x given v actually depends on little x. To summarize, although the event that u is equal to 0 and the event that v is equal to 1 are equal, and both describe the event that the randomly chosen point lies on the diagonal, when we compute these conditional probabilities using conditional densities, we are actually computing two completely different quantities, corresponding to two different interpretations of what it means to condition on the diagonal. This bewildering result is an instance of Borel's paradox. And the first time I saw this, I was blown away. It's a beautiful example which illustrates that one should exercise care when working with events of probability 0. The example I discussed in this video is adapted from exercise 4.11 in Probability and Random Processes, a great book I recommend you check out if you want to learn more. In closing, I hope that you've enjoyed this video and that its contents inspire you to dive deeper into the fascinating world of probability theory. Thank you.